So until the previous lecture, we were worried about how to simplify logic expressions, right? So our first strategy was, let's do it using Boolean algebra. And when we did that, it was okay for simple expressions, but as the expressions got more and more complex, the Boolean algebra also got complex. And there were a few issues with Boolean algebra. One was there were several ways of going about it. And the second major issue was there was no good way of knowing whether you have arrived at the simplest answer or not. So if you're doing some Boolean algebra simplification, then you could be facing a situation where you get to an answer and you really don't know whether it is the simplest or not. And that is usually the case when you have more variables in the logic expression. So we moved on to K-maps. K-maps gave us a very systematic approach to logic simplification, and because it was a graphical view of a truth table, things got relatively easy, and we were able to tackle K-maps going from 2 variable K-maps all the way to 5 variable K-maps, both for simplest sum of product expression as well as for the simplest product of sum expression. And you guys have seen this. You've gone through exam 1 on this, and I suspect that most of you feel very comfortable with the idea of K-maps because it's following a set of rules that has been laid out. And if you follow the rules with the main objectives in mind, the main objectives being make as big of a group as possible, which will lead to as fewest number of groups as possible, you will be okay. All right, so the next idea that we are going to be talking about is when we have these logic expressions, could there be a problem? And it turns out, because of this is the villain in this chapter. The villain or the bad guy is gate delay. So due to gate delay, we will have some problems in how the output of the logic diagram behaves, which is going to be different from what we expect. And the culprit is gate delay. So we'll take a look at glitches and static hazards. We will be focusing on their detection and their elimination. So for elimination, we will be focusing on a specific type of static hazard. We will be focusing on static hazards for elimination, but we will take a look at how to detect various other types of hazards as well. To help with what we are going to learn in this lecture here, I am defining a few keywords that will help us have this conversation about glitches and hazards. And we have been informally thinking about these things, but now we are formally talking about prime implicants, essential prime implicants, and redundant prime implicants. So what is a prime implicant? A quick disclaimer over here. I am focusing on combining the ones in these 3 definitions. So essentially, I'm talking about sum of product prime implicant, sum of product essential prime implicant, sum of product redundant prime implicant. But I will be focusing on sum of product versions. You can switch it around from ones to zeros and start looking at combining the zeros, and you will be in the product of sum version. So what is a prime implicant? A prime implicant is a product term, because we are looking at sum of product, a product term that is the result of all possible groups of ones, right? Not what is the least number, but all the possible groups of ones will be the set of prime implicants. In this case, because we are combining the ones, these will be called sum of product prime implicants, or SOP PI. So we can write this over here. Prime implicants. But we have to be careful over here about breaking a group of 4 ones into 2 groups of 2 ones is not allowed. So what this means is I cannot be taking a group of 8 ones or 16 ones and break them into smaller groups and then call them prime implicants, because they're also possible groups. So those are essentially not counted as unique prime implicants. So that is not allowed. I cannot break a bigger group into smaller groups and then call them different prime implicants. That is not allowed. But all the other unique possible groups, yes, that is going to be prime implicants. So let us look at the PIs, or prime implicants, in a little bit more detail. So take a look at this 3 variable K map over here at the top. If you were asked to find the simplest SOP expression for this, you would probably say, let me use blue here, sorry. You would probably say, this is my group here, this is my group here, right? And that's it. You would say these two are the simplest. And those would be, let's see, if I can do this. This would be what? A complement and C complement. And for this guy, you might get BC. Those are the two. But because we said prime implicants are all possible groups, then I have one more that I could include in this conversation, which is right here. Let me highlight this in right there. So the one that I highlighted in red is also a prime implicant, because this is also a possible group. And I'm not breaking a group into smaller groups. So this counts. So I'll say this guy is what? A complement and B. So we have 3 prime implicants in this example. You've got one here, you've got one here, and you have got one here. Notice I did not make one group here and one group here and call them prime implicants, right? So because that would be breaking up a group of 2 into 2 singletons and naming the PIs. That is not allowed. But all the other possibilities, yes, it is allowed. So we have 3 prime implicants in this case. Next, what would you do for the K map, 3 variable K map at the bottom? Are there any groups of 4 ones? 8 ones is not there. So the next question is, are there groups of 4 ones? So you would probably say that this is one group of 4 ones. Is there any other group of 4 ones? Well, clearly edges wrap around, so you should be able to say, all right, I have another group here, which is that and that. So if I name them, what do I have? Let's see. This guy is going to be B is 0 and C changes, A changes. That's B complement. And over here, that is going to be A complement. So in this case, I only have 2 prime implicants. There is nothing more I can do. I have that. Those are all the possibilities. Because remember, I cannot break up a group into smaller groups. So I can't do that. So two prime implicants over there. Let's talk about this. Any ideas about how to start thinking about this? Start thinking about what would be the simplest sum of product expression if you had this four variable K map that you see over here. What are some things you could do? Are they groups of any? Are they groups of 16 ones? Clearly no. Are they groups of 8 ones? No. Are they groups of 4 ones? Still no. Are they group of 2 ones? You can see that there are several groups of 2 ones. So one strategy could be to combine them as horizontals. So you could do 1, 2, 3, and 4. So 4 horizontal prime implicants. But also 1, 2, 3, 4 vertical prime implicants. So in this case, we have got, let's see, I'm going to simply write it maybe over here at the top. 4 horizontal prime implicants and 4 vertical prime implicants. So in total, I've got 8 prime implicants for the third example. So I hope with those examples, we are okay, we are comfortable with the definition and how to identify sum of product prime implicants. And if you switch it around to sum terms, they will be POS prime implicants. Just focus on the combining the zeros. All possible groups of zeros. You cannot break a group into smaller groups. All right. So that's a prime implicant. Now we are going to have a classification of prime implicants. We are going to call this next one essential prime implicants. The definition of essential prime implicant is if there is at least one in a prime implicant, it is an essential prime implicant. What does that mean? Go back over here. What were the prime implicants from previous example? 1, 2, and 3. There were 3 essential prime implicants. Now, look at the ones. I'm going to highlight the ones that are only in one group. So let's see. This one is only in that particular horizontal group. And this one is only in that particular horizontal group. So those two would be essential prime implicant. Essential prime implicant. And the vertical group that you see over here, the ones there belong to more than one group. In this case, 2 groups, which means those are not essential. Not EPI. I hope you see um, the definition being at work here. In other words, even if you were to remove the non essential prime implicant, you would still have full cover on all the ones. How about here? How about the second example? Second example, what we did was, let's see, we said that was one group and that was one group. And these ones are only in one group of ones, and these ones are only in one group of one, which means that both are EPI. Both prime implicants are essential in this case, because even if I remove one of them, I would have some ones that are not covered. All right, now let's talk about this. In the examples earlier, we said there are 4 horizontal prime implicants. So 1, 2, 3, and 4. And then we said there are 4 vertical prime implicants as well. So, and now the question is, and I will leave this to you guys, are there any essential prime implicants in this case? Brilliant. No essential prime implicants. Because all the ones belong to more than one group. So I hope that you guys can see. Well, let me do the color coding here. Color coding is all of this, right? Two groups, two groups, two groups, two groups, two groups. So that's how we identify prime implicants and essential prime implicants. Next, redundant prime implicants, right? That is what is left over. So a redundant prime implicant is going to be a group in which all the ones belong to more than one group. Keyword here, all the ones belong to more than one group. So what do we have here? In terms of our examples, we have, let's see here, group 1, group 2, or I should say prime implicant 1, 2, 3. Which one is redundant? The one that is redundant is the one that is in the middle. So let me use a different color, perhaps green here. That guy is redundant because all the ones in this case belong to more than one group. How about over here? One group was this guy, one group was this guy. In this case, you have no redundant prime implicant. How about over here? Horizontal, vertical. Come on. In this case, you can say all of them. all 8 redundant prime implicants are, all 8 prime implicants are redundant prime implicants, because all the ones are belonging to more than one group. All right. So I hope for the second example, why are there no redundant prime implicants? So you see this? For the second example, there are two groups. One is this guy, which was A complement, and the other was this, which was B complement. A complement has these two ones that belong to only one group. So it cannot be redundant because it is essential. And the second prime implicant group for B complement has these two guys that belong to only that group. So it is essential. It is not redundant. So both the PIs in this case are essential. Do you see it? All right, wonderful. Let's see. Let's move on here. So that was my goal, to introduce these three terms to you, and hopefully with this we can tackle the glitches hazards topic very well. Let's move into it. This is going to be like the most fundamental discussion of today's lecture. As simple as a function which is x or x complement. So if I didn't show you any of these diagrams below, and I just said f equals x or x complement, what would you say that equals? X or x complement. Using Boolean algebra, you would say x or x complement should be a 1. Absolutely. No matter what happens, f should always be 1. Okay, so that's what we know from Boolean algebra. Let us see what happens when you actually make the connections on a piece of hardware and observe the output. Right away, I hope you can see that the function over here is going to 0 at certain times, which means there is some problem going on. And that problem is referred to as the glitch. So let us see why this happens. Well, let us start with input. What is this? This is essentially showing a square wave. What does that mean? That means that this has the ability to generate zeros and ones. Maybe they are periodic, 0 1 0 1 0 1 as an oscillator, or they could be switches which are manually being turned off and turned on, similar to what you do on your basis 3 board. So let's see. If this is 0, and let's tackle this, right? Let's take a look at this time. Say this is t0. So we have x is what is x? X is a 0. X is a 0. X complement is a 1. And what is f? F is also a 1. Let's just see that. So x is a 0. And if this is a 0, this will be a 1. And because this is a 1, f will be a 1. right? That's at time 0. Let us move forward here. Let us take a look at what happens when you change x from 0 to 1. So let's see over here. So at t1, x is being changed from 0 to 1. The top one is x, the second one is x complement, the third one is f. So when you change x from 0 to 1, this guy has changed, right? It was 0, it became 1. So this input from changed immediately right here because it is on the same wire. But what about this guy? Does that change immediately? No, it will take some time. Why? Because of the gate delay of this NOT gate. So it is going to take a very small, but still there is going to be some finite time delay, gate delay of the NOT gate. That is why the x complement changes from 1 to 0 slightly after the change in x. But you see what happens during that time, f continues to be a 1. That is great, right? During that time, f continues to be a 1, which is what we expect. So this continues to be a 1. Really good. And what made that happen? The thing that made it happen was x complement remained 1 for that short duration of time, which was the input to the OR gate, so it kept it at 1. That was good. So we got saved because x complement was 1. It was true. Now let's go a little bit further. Let us try to take a look at over here. Let's see. I'm going to take a look at a time t2 over here, where x has gone from 1 to 0, but x complement is going to take some time to go to 1. So what is going to happen there, right? So this is now, it has changed. It is 0 here. Before t2, it was 0 there. This was 1 there, right? So we are starting with this now. We are saying this is 1, this is 1, this is 0, so that is 1, right? That is the condition before t2. Then we change it. We change this guy to 0. So right away, this goes to 0. But you see this 0 to reflect a change over here to 1, it is going to take this much amount of time, gate delay. So during that time, we are essentially doing 0 or the previous 0, which means during that time, you have this as 0, which is the problem. That is reflected over here, and I will draw it in a slightly different, maybe pink, right there. Maybe it's all of it, right? Because let me see this. The x changes from 1 to 0. X complement takes some more time to change from 0 to 1. And because there is also a gate delay of the OR gate, f will have an accidental 0 after some time. So this particular condition over here is called the glitch, and that is specifically an accidental 0. Because we didn't want 0, we wanted a 1, but we got an accidental 0 because of the gate delay of the NOT gate. And similarly, you see the glitch 2 more times, but more importantly, you see the glitch when the input changes from 1 to 0, right? You are seeing that glitch over here, over here, over here. What you can say is you get an accidental 0 or glitch when x changes from 1 to 0. It is not the other way around. When the input goes from 0 to 1, there is no glitch, because when it is going to go from 0 to 1, the other input x complement is maintaining the output at 1, so it is taking care of it. So it is the nature of this OR gate that is allowing us to preserve the output. And this discussion is important because this is going to relate to sum of product hazards and product of sum hazards, and the fact that they only happen when the input changes from 1 to 0 or 0 to 1 for the other case, for POS. But it only happens at one change, not both changes. And that's due to the nature of this OR gate, or for POS, it would be the AND gate. All right, questions about this discussion? This is essentially at the core of this chapter. All right, let's move on here. For the sake of completeness, let me point out a few things. The top scale over here is a time scale indicating nanoseconds. So we have 20 nanoseconds, 40 nanoseconds, and so on. What we are more concerned about is the timing diagrams of x, x complement, and f. And you see the accidental zeros happening over there 3 times. Okay, let's continue. So let's talk about a glitch in a slightly more formal way. A glitch is an unwanted transient in a circuit. In the previous example, the unwanted transient was the accidental 0. So that's a glitch. So it only happens in the transient, right? It is only caused due to the input x changing from 1 to 0, as we saw earlier. So it's about a transitioning state as opposed to a steady state result. So if x remains the same, then there is no glitch. When x changes from 1 to 0, then there is a possibility of a glitch. So which is different from expected steady state result. The expected steady state result in the previous example was f should be 1 all the time, no matter what x is. That was the steady state result. All right, so sometimes the glitch is called logic noise. It is caused by the propagation delays and the timing defects in the combinational logic circuits. So it's more specifically, it's not the propagation delay, it is the specifically gate delay. So the gate delay is what causes, I should say, it could cause a glitch in that case. Now, I hope that you are questioning this, right? Why is he saying it could happen? Well, the glitch could happen because x could go from 1 to 0. But x is a user input. So if the user says, I will have it at 0 and I will never change it, then glitch will never happen. If the user says, I will have it at 1 and I will never change it to 0, glitch will never happen. If the user says, I will have it at 0 and I will only change it to 1, glitch will never happen, right? So there is a possibility of the glitch in general, but it will only happen if the user decides to change the input from 1 to 0. That is the reason why I'm saying there is a possibility. All right, let's move on. Glitches come from a German word which means a slip or error. A hazard, so how are glitches and hazards different? A hazard is present in a circuit when a glitch can occur under some input conditions. And the input condition that we talked about just now was x changes from 1 to 0. So that was the condition in which the glitch could occur. And because a glitch could occur, a hazard is present in this circuit. So you could say that is the glitch, but because we have observed that an accidental 0 is possible here, you could say a hazard is present. All right, so that was the definition of glitch and hazards, dealing with them a little bit more formally. I can perhaps highlight some keywords here. Hazard and glitch. Let's see. Propagation delays are important to highlight over here. And then transient, of course. All right, let's move on. Maybe this one is. So I touched on this a little bit early, where we have two different types of delays. One is the propagation delay, and the other one is the gate delay. Propagation delay refers to the time delay between an input changing and the output of a circuit changing, right? So time it takes for a change in the input to affect the output of a circuit. So it's the overall circuit. But for a gate delay, it is the input of a gate to the output of a gate. So it is with respect to a gate. Time for a change in the input to cause a change in the output of a gate. Right? So you can clearly see that the gate delays should be much smaller than the propagation delays, because the circuit will have usually more than one gate. Gate delays is the primary component of propagation delay. Other contributors could be wires, and if you want to keep the propagation delay to a minimum, then you have smaller gate delays and smaller wire delays by keeping components close to each other. And the digital designers who design PCBs, they design for the worst case delay. Meaning, if a designer is connecting one component to another component, say on a PCB, right? So let me call this component 1, component 2, right? And if they have to draw wires, or trace a wire from one to the other, and let's say that one wire can go straight through, and the other connection that needs to be made is from here to here, because the pins on those chips are, say, on the other side. If that is the case, then they will have to do this, right? But the problem is that the delay over here is much smaller than the delay in the second connection. And digital designers, they have to be very aware of this, because it is often required that suppose you have a bus, not one wire, but you have a bus, right? Similar to in VHDL, what do you say? You say 7-bit vector, right? Or a 6-bit vector, whatever. say 4 wires together. That's a bus. And if you need so obviously you're calling them a vector or a bus, which means that all these changes need to be happening at the same time. And if all these changes need to happen at the same time, the wire delays should be consistent. All the 4 wires should be of consistent length. But because you are doing this on a printed circuit board, you might not be able to do that because of the nature of where the pins lie. And of course, all the other things that are around these chips, right? You might have other things that are around here, which makes that job very difficult. So digital designers, what they do is this is almost an art form. They draw wires from one component to the other while obeying printed circuit board laws, and they try to make all the wires of equal length. So they will use techniques like they will go around something and then they will come down like that, right, for 2 wires. There will be limitations on, depending on the speed of the signal, there will be limitations on the angle at which the wires can bend. And of course, we have been talking about the lengths. We have to make those lengths consistent and so on. So the digital designer, Charles says, is that why? Yes, it is. That's why we have all those squiggly traces. Because at very, very high speeds, even a small difference in length matters a lot. So if you look at a very slow application, then you might not see those squiggly traces. But if you see a very high speed application, then you will see those squiggly traces, right? And computers, RAMs, and all the PCBs that you find in a computer, all those are high speed operation. So you will see those squiggly traces there. And one of the main goals is to have all their lengths equal. So it's more of an art form than it's due to an engineering issue, but it's almost art the way they do it. All right. So I hope that discussion was helpful, and all of this is to tackle one villain, right? The villain being the gate delay. Okay. What are the kind of hazards that we are going to focus on? We are going to focus on 3 different types. One is the static hazard, dynamic hazard, and the function hazard. So a static hazard is the simplest one of them all, and we will be looking at how to detect it, and we will also focus on how to eliminate a static hazard. Static hazard is present in a circuit where there is a glitch that occurs in a logically steady state 0 or 1 or one output when a single input changes. So static hazard refers to a single input change, like we had in the example that we looked at. X was changing from 1 to 0, and that was the problem. What this means is, if you have a circuit in which there are more than one inputs, you cannot, so to observe static hazards, you will not be looking at changing all the inputs. You will be leaving all the others the same and only changing X. So it's about the output behavior when a single input changes. Now, they are of 2 types. Static hazards can be classified as a static 1 hazard. Static 1 hazard is also called as a sum of product hazard. It is the hazard condition in which an accidental 0 could occur. This is the example that we just saw earlier. Another option is a static 0 hazard. Static zero hazard is also called as the product of sum hazard. And this is a hazard condition in which an accidental 1 could happen. So you are expecting a 0, a 1 occurs, right? That's an accidental 1. So those two are static hazards, and we will be taking a look at detecting, eliminating static hazard. There are other types of hazard as well, dynamic and function. Dynamic hazards are multiple transition glitches that occur in a multi-level circuit. It is still single input, but if a single input goes through multiple paths to the output, 3 or more delay asymmetries in the path to the output, what is going to happen? Well, if the single input changes one time, those changes will reflect at the output at 3 or more different times, right? So because they are timing asymmetries, the one change could result in those changes arriving at the output at multiple times. So that is going to possibly result in a multiple transition issue, and those are dynamic hazards. So for dynamic hazard, we will only look at an example, but we will not look at how to eliminate it. So we'll focus on detecting it. Next, function hazard. Function hazards are the most difficult to detect and eliminate. The reason is, in this case, we are not limiting things to only single input. This is going to be when 2 or more inputs to a gate can at almost the same time make a glitch happen. So a glitch occurs when 2 or more inputs to a gate change at the same time. Right? So we have been focusing on holding one input and changing the other input. But what if you change both inputs at the same time? There will be glitches that occur due to that. Those are classified as function hazards. So again, for function hazard, we will take a look at an example related to the detection of it, but we will not go into eliminating function hazards. Let's take a look at static hazard. Static 1 hazard. What else can we call this? Static 1 hazard or SOP hazard, or we can call this accidental 0. Now, right away, you might be able to relate to the term SOP hazard. Why is this SOP hazard? Because it is a sum of products. There are multiple AND gates that are feeding into an OR gate. So you have a sum of product expression, XZ complement or YZ, that's a sum of product expression. And when you lay it out in terms of a circuit diagram, that's what you have. So that's why it's called a sum of product hazard, which is also a static 1 hazard, because you will be focusing on, if you look at it in terms of a K-map, which is possible here, you will be focusing on grouping the ones there. And that could result in a accidental 0. As you can see over here, there's accidental 0 happens there. Now, let's take a look at what is expected, right? The expectation is, if you have this equation, XZ complement or YZ, I can say this particular statement by just looking at the logic expression. F should be 1 when both X and Y are 1 and Z is 1 or Z is 0. So if X and Y are both 1, no matter what Z is, F should be 1. In other words, if I hold X and Y at 1 and I change Z, F should not change. right? So that's what is expected because of this particular logic expression. As long as you change only z, hold x and y, f shouldn't change. Let us see if that is the case. I'm going to erase my highlights here and then show you how we are holding x and y. In the timing diagram, x is here, y is here. We have made x1, we have made y1. As you can see, all throughout x is 1 here, all throughout y is 1 here. But z, we are changing. Z is 0 here, then changes to 1, changes back to 0. Right? So z is changing. And then if you go back here, x is 1, y is 1. Over here, the product is what? This is x and z complement. Over here, the product is y and z, because this is z and this is z complement. Or z prime. The p stands for prime. Z prime or z complement, they are both the same thing. The complement of z. So z is changing. 20 nanoseconds it is off, 20 nanoseconds it is on, and it is periodic, square wave. Now, as z is changing, what would happen to z prime or z complement? That was also going to change. But because of the gate delay of the NOT gate, things will change slightly later, right? So if z changes from 0 to 1 over here, z prime changes from 1 to 0 at slightly later time. And then there will be changes at the output. But what is going to happen is this. When you change, let's take a look at this. This is z here. This is z prime here. What is this? This is yz. And this is xz prime. All right, I'm going to zoom in over here. And just for the sake of identifying these 4 timing diagrams, I have labeled them over here. And then, of course, the last one is f. Z changed from 1 to 0. Let me draw this using that time. Z changed from 1 to 0. At a slightly later time, Z prime changed from 0 to 1. But between those times, there was a time when Z and Z complement was a 0. During that time, Y and Z, because Y was 1, during that time it was still 1. So Y is 1 all those times. So Y and Z is 1. But it goes to 0 because change in Z is there. It goes to 0 slightly later because of the gate delay of the AND gate. Right? This changes over here. This changes over here. That's due to the gate delay of the AND gate, Y and Z. Then how about X and Z complement? X is 1 all the time. Z complement just changed from 0 to 1. So X Z complement goes from 0 to 1 at a slightly later time than this, because again there is a delay, gate delay of the AND gate. Now F is simply the OR of this. So if you OR everything out, what do you get? Well, you get 0, let's see, this and this, right? So 1 here, 1 here, 1 here. But during this time, you see the problem time is here. When you add those two up, you are going to get a 0. So F is going to be a 0 at that particular slightly later, because there is also a gate delay of the OR gate. So what does that tell you? This is essentially an accidental 0 that is happening because of a change in Z. And again, only when Z changes from 1 to 0, that is the static 1 hazard that is present in this circuit. So glitch when Z goes from 1 to 0. But when Z goes from 0 to 1, this doesn't happen because of the nature of the OR gate. OR gate, if it has multiple inputs, as long as the other inputs are holding the output to 1, it doesn't matter. Going to 0, that's when the issues are going to be there. There's a question on the chat box. Let me read that. Is this particularly the case? Yes. This is exactly situation the same as the break before make switch, Charles. It's related to that. So the underlying concept is the same. All right. So I hope that was a helpful exercise. Now, before I move further, I want to shed some more light on this particular example. Essentially, I want to see how we can fix this. Right. So let me add one more slide here after. Sure. And I will consider my function. What is that? F was x z complement. X and z complement, or y and z. And I'm trying to fix the static 1 hazard. So what I'll do is I'll start off with a 3 variable K-map. And I'll have 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. I have x, y, and z here, right? So this is my skeleton of the 3 variable K-map. And as you can see, this is what? This term is x is 0, x is 1, z is 0, and y is 0 or 1, right? So x is 1, where is x is 1, y is 0. So it is there, and x should be 1, right? And then, so the second one, y equals 1, z equals 1, x equals 0 or 1. So y, z, let's see that. This one, and x is 0, this one. You guys okay with how I transitioned the logic expression into a K-map? So this would be a good time to ask any questions if you guys have it. How did I take the expression and go into K-map? All right, looks like you guys are comfortable with this. So let's look at the prime implicants here. What are the prime implicants? Prime implicants are 1, 2, which is 1, 2. Is there a redundant prime implicant? That is the redundant prime implicant. What is that? X and Y. Meaning, if I rewrite this function as x and z complement, or y and z, or x and y, this is my redundant prime implicant. Because of this. Did I fix the hazard? Yes. You see this? I have essentially fixed the static 1 hazard. How did I do that? You see this? When x is 1 and y is 1 and z changes from 0 to 1 or 1 to 0, there was no cover. Now I have covered that with a group. So I have fixed that hazard. You see this? I'm referring to these two being 1 and this changing from 1 to 0. The static 1 hazard was happening when x was 1 and y was 1 and z was changing from 1 to 0. There was an accidental 0. And now we have added that redundant prime implicant. So we have covered that situation. So as long as x and y are both 1, one of the inputs to the OR gate will always be held at 1. So no matter what z does, this is independent of z. So no matter what z does, you will have the output at 1. Now, I hope you are asking the question, did I change the logic? No, you have not changed the logic. If you can easily try to prove that this function f here is the same as this function f here. We have actually just made it, so we have gone from simplified expression to the non-simplified expression, right? So we have essentially made the big logic expression more complex, but we didn't change the logic. You see, we did not add or subtract any zeros or ones in the K-map. It is as is. So without changing the logic, we were able to fix the hazard by adding one more AND gate, which is x and y, to it. Because the problem was that z, when it was changing from 1 to 0, was causing trouble. So we made a product term which is independent of z, and we fixed that solution. We fixed that static 1 hazard problem. And it relates to the K-map this way. That is essentially adding the RPI. Here is the fix. Same logic. The top, this is the fix. This one is xz complement. This one is yz. And in red, I can write x and y over here. So even though the input z changes the same way as before, f is not going to f is going to continue to be 1. It is never going to go to 0, because this term, as long as x is 1 and y is 1, x and y will always be 1. So even though this changes and this changes, this guy is always going to be a 1, the middle input to the OR gate, and that will help f remain at 1. One thing that is critical in this is for you to notice we did not change the logic, right? We did not make it into a different expression. We just made it into a simplified to a non-simplified version of the same logic expression. All right, so let me see this way. Couple of questions. So basically, adding redundant groups of ones can eliminate the glitch. You are right, Michael. By adding the redundant prime implicants, that's how we fix the glitch. But each fix will be related to each condition that we are trying to fix. And I will, when we go to a 4 variable example, I will talk more about that. There's another question. Do you have to add in every RPI case to eliminate glitches? Yes, you do. An example, a little bit more complicated example, we will see there, where you can clearly map, this is the RPI I am adding to fix the static hazard which was happening due to this particular input condition. So so here you can say the condition. What is the condition here? The condition is glitch. No, not glitch. We can say an accidental zero could happen when z changes from 1 to 0 while x is 1 and y is 1. So that's the condition. The condition is z has to change from 1 to 0, not the other way around, 1 to 0 only, while x is 1 and y is 1. That was the accidental 0 that could happen. And the fix is on this side. Fix is add RPI, x and y. So that is independent of z, and now even if z changes, you are done. You will be okay. So as you observed in F over here, no accidental 0. It is going to be 1 the entire time. So in a more complex example, you can literally write these kind of input conditions and add RPIs to counter each of those input conditions. Okay, so we added one gate, right? So we added one gate. Let's see. One gate was added here, which was that guy, and we were able to fix it. So a little bit more costly, right? It's not the simplest, but the good news is that it is glitch-free equivalent circuit. Now I want you guys to notice one more thing. Where have you seen these two before? This and this. Where have you seen this before? Yes. Boolean algebra properties 17a. So that is the simplification theorems that we used and proved and all that. So you know logically you didn't change anything for sure because it's a theorem. We proved it. All right, let's move on here. Let us talk about a dynamic hazard. A dynamic hazard is one input changing. In this case, x is changing. We are leaving w at 0, y at 0, and z at 1. So we are leaving the three other inputs to this circuit the same. We are not changing it. We are changing only x. However, there are multiple paths to the output. So you see x, changes in x could reflect to the output this way, or let me use pink here, this way, or this way. So you see there are three different paths that are that you have to go to the output with the same input x changing. So what could happen here? if you have this function f, written it up in the sum of product form as this is essentially a logic expression that is related to the logic diagram over here. Notice there is a 4 nanosecond gate delay due to the OR gate. Now there is a NOT and then OR, there's a 8 nanosecond delay over there. Over here there is also a NOT and then a AND, so there's a 8 nanosecond delay over there. There's a 4 nanosecond delay over there. So you have multiple delays in that path, which is what we are calling that, right? We are calling that as the delay asymmetries. So you have 8 here, we have 8 plus 4, 12 here, you have what is this? This is simply 8 here. So if that is the function, you leave w as is, you leave y as is, and you leave z as is. So you're literally keeping this the same, this the same, this the same. You're only changing x. Only one input changes. F is going from 1 to 0. But how does it look like when x goes from 0 to 1? How does it look like in terms of a timing diagram? That change gets reflected at the output multiple times, at multiple times. So f has to go from 1 to eventually 0 in steady state, but it goes from 1 to 0 to 1 to 0. You see, the changes are going to happen multiple times, so multiple transitions at the output. This is the 1 over there, that is the 0 over there, that corresponds to that and that, but it doesn't go straight from 1 to 0. It goes from 1 to 0 to 1 to 0, right? So that is due to the timing asymmetries, and that is dynamic hazard. Dynamic hazard means output giving you a wrong output as a result of only one input changing, others are the same, and in the case where there are 3 or more timing asymmetries to the output. We are essentially looking at it, we are not eliminating dynamic hazards. Let us go on to the last category here. This is function hazard, in which 2 inputs change at the same time, and there is absolutely no easy fix for this. Excuse me. The example that we are seeing is over here you have x that changes, over here you have y that changes, you have f equals x or y complement, and because it's a simple expression, you can analyze it very quickly. You can say f is going to be 1 when x is 1, y is 1, or when x is 0 and y is 0. So when both of them are the same, f should be 1. But what if those the things that are same, if you change x and y at the same time, what happens then? Well, you can see that if x and y change at the same time, due to this little NOT gate present, you are going to have accidental outputs over here. You wanted them to be 1. You wanted f to be 1. But you can clearly see that when you go from 1, 1 to 0, 0, you got an accidental 0 there. So that is function hazard. X and y both change from 1 to 0. F should have remained 1, but it didn't. Again, this goes back to the same NOT gate and the kind of similar concept to a glitch, but now it's with respect to both the inputs changing at the same time. So function hazard, more than one input changing. Dynamic hazard and static hazard, only one input changing. The difference between static hazard and dynamic hazard is, in dynamic hazard you will have more than 3 or more timing asymmetries to the output. In static hazard, it is only going to be a sum of product or product of sum form. All right, so I hope you find that helpful. Now, a couple of terms that we are going to introduce, you already know these things. We are just calling them slightly different things now. You already know these things from the previous discussion. So I hope that just the names of a few things are going to be new here, but other than that, everything should be the same. Let's see. What is a coupled variable? We are going to we are going to see what a coupled variable is, what a coupled term is, what is the residue. And then, of course, the hazard cover is the RPI, which we add. You already saw that in terms of a 3-variable K-map. So if you have that expression, let's say f equals x and z complement or y and z, there is a coupled variable here. What is that? A coupled variable is a variable which is complemented in one term of the output expression and uncomplemented or true in another term of the output. So if you see this, what is the coupled variable here? Z complement. So the coupled variable would be z here. Similarly, over here, if you have x, y, x bar z, x is the variable that is appearing in true form here, in complemented form here. So x is the coupled variable there. Next, coupled term. Coupled term is a term with only one coupled variable. Example, well, both of these are coupled variables, right? So in blue, I can say this is a coupled term, this is a coupled term because they have z and z complement. So both of them are coupled terms. X and y, x and z complement, each of them are coupled terms in x, y or x complement z. Why? Because both those product terms have the coupled variable in them, which is x in this case, or z in this case. So coupled variable, coupled term, let's move on. Residue, whatever is left over, right? So if you remove the coupled variable, you are left with the residue, y, z. Residue is that part of the coupled term that remains after removing the coupled variable. Example, y and z are residues in that. X is the coupled variable, x, y, x complement z, those are coupled terms. Y and z are coupled, are residues. Hazard cover, or also called as the consensus term, is the redundant prime implicant. In this case, that is going to be the product of the residues. Example, y and z in this case. And we talked about what a redundant prime implicant is and an essential prime implicant is earlier on, right? So we are essentially adding a redundant prime implicant to cover the hazard condition. It is also called as the consensus term because it relates to the consensus theorem 17a. Those are the consensus theorem. So this is essentially 17a and 17b from the Boolean algebra properties. And one of them is the SOP hazard, and this is the POS hazard. SOP hazard is present here, gets eliminated here. So SOP hazard is present in the left hand side of 17a. It gets eliminated by going to the right hand side of 17a. POS hazard is present in the left hand side of 17b. It gets eliminated on the right hand side. So what is the coupled variable in both these forms? Let's take a look. X complement z. So x should be the coupled variable. What is the coupled term? X and y, x complement and z. So both should be coupled terms here. And For the POS form, you have the other two, X or Y, X complement or Z. What are the residues? What is left over? Well, let me highlight in green here. This is left over here, this is left over here, this is left over here. Y and Z over here, this is left over here, apart from the coupled variables. So Y and Z will be the residues in both forms. What is the redundant prime implicant for SOP form? YZ, product of the residues, YZ. Y or Z is the RPI of POS form. So by ANDing the RPI in the case of SOP, ORing the RPI of the SOP and ANDing the RPI in the POS form, you will be able to fix the SOP or POS hazard. SOP hazard is also called as the accidental 0. POS hazard is also called the accidental 1. Let us take a look at some examples and you will be able to clearly see how let's turn it into a very simple process. So suppose you have an expression. This is the example of static hazard detection and also elimination. So F is given to us as A complement B or AC, right? So what is the coupled variable here? Well, coupled variable should be A. What are the residues? Residues should be BC. So if you add BC as the RPI, you should fix it. Coupled variable A. The coupled terms are both the terms are coupled. B and C are the residues. So RPI is BC. So the hazard cover, so essentially adding this BC term is the RPI term, you will be able to fix the static 1 hazard. Now that is using the terminology. What is more helpful and can be used in general is the K-map approach. So you take the logic expression and you translate that into a K-map, SOP K-map, right? You are focusing on the ones, you are grouping the ones. So that guy is what? This is A complement and B. This guy is. So that was given to us. F equals A complement and B or A and C. So if you write those two terms as ones and you combine them, the blue guys are the essential prime implicants. Why are they essential? Because this one is only in that group, this one is only in that group. Those are essential. But there is also this red group here, which is the redundant prime implicant, which is the BC term. When you add that, you will cover the static 1 hazard that is possible when, what is happening here? From this to this, A changes, A changes from 1 to 0. A changes from 1 to 0. We have already seen this. For SOP, things are changing the accidental zeros can happen only when the input variable changes from 1 to 0 and not the other way around. So when when A changes from 1 to 0, while B and C are 1, 1. Why is it 1, 1? You can see this over here. Let me highlight in, green. C is 1, B is 1 for both those RPI terms, for both those ones that are in the RPI. So while you have B and C as 1 and A changes from 1 to 0, that's when the hazard is possible, and which we are covering with that red group. So that's your that's the fix. The fix is in red plus BC. Questions here? So the two essential prime implicants that RPI covers is the case that the hazard appears. Yes, that is the case when the glitch could occur. So the hazard is present, right? The hazard is present, but the glitch could occur when A changes from to. So let me write that statement actually. Let me write the input condition so that we can clearly see it. Input condition. For accidental 0. What is it? Glitch could occur. Glitch could occur when A changes from 1 to 0 while B equals 1 and C equals 1. So that's the condition in which the accidental 0 could happen. So it's the red guy. The RPI term is the term that will make the function glitch free. All right, let's do a static hazard detection, but now we are changing the form. We are changing the form from SOP to POS form. Coupled variable A, coupled terms, both of them. Coupled term here, coupled term here. Coupled term, coupled term. Because A is there, A is part of both. What is the residue? Residue would be C, B. What would be the RPI? It would be B or C. So it should be very straightforward. So we have essentially done this. That's what we did very, very quickly. But in terms of a K-map, let's take a look at this. The first term over here, what is in blue, I can maybe talk about this. What is this? This is A is a 1 and B changes, C is a 0. That. And then this guy is what? This guy is both A and B are 0. Once you write the two terms, the two sum terms, then you take a look at the PIs, essential prime implicants and the redundant prime implicants. The blue groups are essential. This 0 only in that group, this 0 only in that group. So now if you take a look at the whatever can be combined even more, you will see that there is a redundant prime implicant, that is the group in red. This will cover the situation where what is changing? Let's see. B is 0, C is 0, A is changing. So A changes from 0 to 1 while B is 0, C is 0. That's when the POS hazard is present, or an accidental 1. So for it's called static 0 hazard, POS hazard, which results in an accidental 1 happens when things change from 0 to a 1 while the other two are the same. In this case, they are both at 0. So you could write a similar statement here, right? You could say the condition is when A changes from 0 to 1 while B equals 0 and C equals 0. That's when the glitch could occur. And you fix that by adding the RPI term. In this case, what is it? B or C, because for both of them, B is a 0 and C is a 0. All right. So similar story, except that now we are looking at the zeros and the product of sum forms. But in general, it's the same story. Also note that this is 0 to 1 change. The previous one was from 1 to 0 change. And this is the POS, right? Or and. So it's the POS forms. Let us do a 4-variable example. You are given, actually, you know what? Let's do this. I think we can continue with this. So this is a 4-variable K-map. We are looking at the sum of product hazards. So let's take a look. Our sum of product expression is given to us as B, C complement, D complement, or A complement, C complement, D, or B complement and C. So if you transition that to a K-map, you have all the blue groups. So for example, this blue group is going to be, let's see, it's a group of 4, so it should be the biggest, simplest. So B complement and C here. For this guy, it would be, let's see, A is changing, B is 1, and C and D are both 0. And for this guy in blue, it is going to be the last one, A complement and C and D. C complement and D. All right. Now try to look at the redundant prime implicants. If you look at the redundant prime implicants, you will see these two. So the input conditions over here are, there is a accidental 0 that could happen when C changes from 1 to 0, when D is 1, A is 0, B is 0. That's one condition. Let's write it down. Input condition number 1 for a glitch to occur. A glitch could occur when C changes from 1 to 0 while D is 1 and A is 0 and B is 0. Right, so that's condition number 1. Next, for the second one, D changes from, when D changes from 1 to 0 while C is 0 and A is 0 and B is 1. So that's your second RPI. So the hazard cover in this case, as you can clearly see, I can actually write the hazard cover there. For the first one, what is it going to be? For the first one, it is going to be A complement, B complement, D, and the second one is C is 0, A is 0, B is 1. So if you add these two guys, what is this? This is the first one, this is the second one. If you add those two terms, we have the hazard cover. Questions about the 4-variable example and how to add the redundant prime implicants. How can we get the direction? Whether one to so here for SOP hazard, the input change will always be, the problem will be only when things change from 1 to 0. Always. Why is that? The reason is SOP hazard will be and all feeding into an OR gate. So when you have a situation where things are feeding into an OR gate, it is very easy to keep things at 1, because all you have to do is have one of them is true, the output will be true. But the problem becomes when the output of an OR gate is going to be 0. That happens when all the inputs are at 0. Well, all the inputs of the OR gate are at 0. That could happen. Well, the problem could happen when only the input changes from 1 to 0 and there is a timing defect in the circuit. So for SOP hazard, the condition will be when the input, one of the inputs is changing from 1 to 0. And the reason behind that is the nature of the circuit itself, right? And it goes back to the first slide that we looked at, right? Not here, here. The first one. The problem was happening only when X was changing from 1 to 0 and not from 0 to 1. Because as you can see, this is, you can view this as a SOP, right? Because at the end it is OR, but there could be multiple AND gates feeding into that OR. So it's the nature of the OR function itself that is the reason for that. And similarly, the story is reversed when you go to a POS hazard. So for a POS hazard, it will be 0 to 1 only, because things are at the end going into an AND gate. For an AND gate, it is very easy to go to 0, right? Because one of the inputs is 0, the output will be 0. But when only the unique condition over here is, in the case of AND, is when all the inputs are true, only then it will be true, right? So it's the nature of the OR gate and the nature of the AND gate logic function itself that is the reason for that condition. For SOP, only when glitch could happen only when the input changes from 1 to 0. In POS, only when it changes from 0 to 1. So if you are looking at SOP, you will have only 1 to 0, 1 to 0. All right, let's move on here. Conditions. Oh, we already did this, right? We did the conditions here. So let me skip over that. Let me copy paste it actually. All right, so simplest forms. This is the same example as before. Simplest form was this. And then RPIs were there. Actually, let's do this example from not from the slide, but in detail. So we are right now we are looking at the static zero hazard, or the product of some hazard, which could cause an accidental 1 in the output. This is the K-map that we are looking at. So let's start with the simplest product of sum. The simplest product of sum would, of course, I can clearly see that group there. So that's easy. Next I have that's easy. And then next I have this. That would be the simplest, right? So you have, let's see, you can say F equals, in blue, you can say, let's see, what is this guy going to be? This is going to be B is a 1, C is a 1, okay, and then for this guy, what do you have? A is a 1, B changes, C is a 0, D is a 1. And then for this guy, you have B is a 0, C is a 0, D is a 0. So the product of sum would be, simplest product of sum would be, let's see, F equals ANDed with one more term. Now, where are the redundant prime implicants in the POS form? There are going to be two of them. One is right here, and the other one is right here. For this guy, it is going to be A is a 1, B is a 1, D is a 1. And for this guy, it is going to be A is a 1, B is a 0, C is a 0. So in red, I can add two more terms. That will give me the hazard free or the glitch free. So let's do a more interesting question here, which is the conditions in which static 0 possibly occurs. A. Let's number them. I will call this guy, well, let me highlight this yellow. So I'll do A in yellow, and then I will do this guy in blue. All right, what is A? Accidental 1 could happen when what is that? What is changing from 0 to 1? C is changing from 0 to 1. C changes from 0 to 1, while D equals 1 and A equals 1 and B equals 1. All right, what is the second condition? B. This needs to be highlighted in blue here to color code them. What is that? In this case, D changes from 0 to 1, while, let's see, A is a 1 and B is a 0, and C is a 0. So the simplest form, and you also have the two redundant prime implicants there. And the second part of this was the conditions in which the static hazard it was possible, and we have laid them out very clearly in form in using words. So this is the same example that you see on the slide over here, but we have done it from start to finish. All right, so let's see. This is a summary slide for our discussion today, which was static 1 hazard. That's when we get an unexpected 0 or accidental 0. And it is only in the sum of product circuits. And we were calling it SOP forms. Static 0 hazard, we looked at the detection and elimination of a static 0 hazard as well, where we get an unexpected 1 or an accidental 1. This is for the product of sum forms. And we fix the hazards by adding the consensus terms, which is essentially grouping the redundant prime implicants. Note also that the complete set of prime implicants will always be hazard free. And the reason is the complete set of prime implicants will include all the essential prime implicants and also all the redundant prime implicants. And because a complete set of prime implicants includes all the RPIs, it will be hazard free. All right, so that's all I have for you guys in terms of glitches and hazards. Let me stop the recording and take questions.